Welcome. Dear students, today we are going to discuss Huckel's rule. Before discussing Huckel's rule, let us discuss what is aromaticity. Aromaticity is this pi electron delocalization in a ring. What is aromaticity? It is the property. Aromaticity is the property of delocalization of pi electron in a ring. Okay, so what are the requirements of aromaticity? There should be a ring, there should be pi electrons, that pi electrons are to be delocalized. Okay, homogeneous delocalization is to be there, that is ample delocalization should be there. What are the requirements? There should be a ring, there should be pi electron, all these pi electrons are to be amply delocalized, right? There should be ample delocalization. This system, this aromaticity, this property brings great stability to a compound. It brings a great stability. This stability is referred to as the resonance stabilization. And this stability is not seen in aliphatic compounds of same molecular weight. So that is what makes aromatic compounds different from that of aliphatic. That is, aromatic compounds have great stability. Why? Because there is delocalization of electron in the ring. And there is a pi cloud above and below the plane of the ring. So therefore they are greatly stable. Okay. No electrophile can come and attack the system because the electrons are delocalized. Now let us come to Huckel's rule. Huckel's rule. How Huckel's rule sets conditions for aromaticity. It gives certain conditions for aromaticity. Eric Huckel, in the year 1931, he brought out a theory. That theory is referred to as the theory of modern aromaticity. The theory of modern aromaticity. In this theory, he is setting some conditions for aromaticity. What does he set? Some conditions for aromaticity. What are the conditions for aromaticity? Let us see. Number one, it should be conditions for aromaticity. Number one condition, it should be cyclic in nature. The compound, it should be cyclic. It should not be a straight chain compound. It should not be straight chain, because in straight chain compounds, ample delocalization of pi electron would not take place. So it should be a ring where there is ample distribution of electron is possible. How is a pi bond formed? Do you know that? Yes, a pi bond is formed when overlapping of p orbitals takes place, right? So there should be ample overlapping, right, and that would lead to ample distribution of the pi electron. Ample overlapping is only possible if it is a ring. So it should be a cyclic compound. The second requirement for this is it should be planar. It should be planar, and all carbon atoms of the ring, all carbon atoms of that ring should be sp2 hybridized. sp2 hybridized. So let me draw one molecule. Okay, this is one molecule. If you can see this carbon atom is sp2 hybridized. This carbon atom is sp2 hybridized. There is a double bond here. This carbon atom is sp2 hybridized. This carbon atom also is sp2 hybridized. This carbon atom and this carbon atom, these both are sp3 hybridized. These both are sp3 hybridized. See, it is a single bond. There is no double bond. So these carbon atoms are actually sp3 hybridized. Now what is the shape of sp3 hybridization? Yes. What is the shape? Tetrahedral shape. Okay. So groups are arranged in a tetrahedral shape here and here. Tetrahedral shape is, it's like this. It's a 3D shape. It's a 3D shape. So this molecule is not at all planar, right? This molecule is not at all planar. So ample delocalization is not possible. overlapping is not possible here. So ample delocalization of electron is not possible. So it does not fulfill second condition. It's not at all planar. Therefore this compound is not aromatic. It is not aromatic because here two carbon atoms are in tetrahedral shape. Planarity goes. So therefore this compound is anti-aromatic. Now let me give you another example. Let me tell you why, if not planar, why delocalization of electron won't take place. Let me give you an example of this example. Look at this. This is 1357 cyclooctatetraene. Cyclooctatetraene. Actually, this is the structure that we write it on the board or on the paper. Actually, its structure is like this. This is the actual structure of this. This looks like a cat's head. This is the actual structure. Now this is the actual 3D structure. This is not at all planar, and being not planar, it is not aromatic. Okay, because it is not planar, it is not aromatic. What is the problem if it is not planar? Let me rub the double bonds here. And let me draw the p orbitals which have not yet overlapped with each other to make the double bond. Look at this. Do you think that efficient overlapping, sideways overlapping is possible in this? No, efficient sideways overlapping is not possible in this. Therefore, ample delocalization of electron is also not possible. So therefore, it is not at all aromatic. Right? It all started from planarity. Okay, this was not planar, right? sp2 hybridized, but it was not planar at all. And because it was not planar, delocalization, overlapping of p orbital did not take place here efficiently, and therefore delocalization of the pi electron did not take place here effectively. So therefore this compound is anti-aromatic. So this is the second condition. The third condition for aromaticity is it should be conjugated. The ring should be conjugated throughout. So we have seen one example of this. I gave you an example like this, right? I have drawn. So this system is not conjugated throughout. This is anti-aromatic, right? Now the fourth rule is that pi electrons in ring, it should be equal to 4n plus 2. Should be equal to 4n plus 2. Now this is Huckel's rule. Okay, these are the conditions. This specific fourth point is the Huckel's rule, that the pi electron in the ring, it should be equal to 4n plus 2. N can be any whole number. It can be any integer. So it can be 0. If you are putting 0, you get 10. If you are putting 1, you get 6. 2, you get 10. 3, you get 14. And 4, you get 18. So you can say that cyclic compounds, planar cyclic conjugated compounds that are having 2, 6, 10, 14 or 18 pi electrons, only they are aromatic. What are the numbers? 2, 6, 10, 14, 18. These pi electrons, they are only aromatic. Let us understand Huckel's rule with examples. Let me first take benzenoid compounds. The first example that I would like to take is the benzene itself. Let me draw the, yes, like this, benzene itself. Now, is it cyclic? Yes. Is it planar? Yes. Is it conjugated? Yes. How many electron it is having? One double bond has 2 electrons, 2 pi electrons, so it is having 6 pi electron. So you can apply Huckel rule, 4n plus 2. So 4 into 1 plus 2, that would be 6. So it satisfies Huckel's rule. The pi electrons in the ring is equivalent to 4n plus 2. Therefore, this would satisfy Huckel's rule. Let us take another example. Naphthalene. What are the questions? Is it cyclic? Yes. It is planar? Yes. Is it conjugated? Yes. How many electrons are there? 10 pi electrons. Can you apply Huckel's rule in this? How much will you put here? 2. N will be 2. If you are putting N into is 2, you will get 10. So the pi electrons in the ring is equal to 4n plus 2. This also satisfies Huckel's rule and other 3 conditions. Therefore, it is aromatic. Now, let me draw the third example before you. This is anthracene. How many electrons here? 14 pi electrons are there. Is it cyclic? Yes. Is it planar? Yes. Does it have a conjugated system? Yes. Do it satisfy Huckel rule? You can put here. What will you put here? Yes, 3. If you are putting n is equal to 3, you will get 14. So this also satisfies Huckel's rule and other 3 conditions. Therefore, all these benzenoid compounds are aromatic in nature. Now let us go to benzenoid compounds having heterocyclic atoms or benzenoid heterocyclic compounds. Benzenoid heterocyclic compounds, that would be class 2. Okay. Now see the case of pyridine. See the case of pyridizine. This is pyridizine. Is it cyclic? Are they cyclic? Yes, they are cyclic. Are they planar? Yes, both are planar. Are they conjugated? Yes, both are conjugated. How many electrons here? 6 pi electrons. How many here? 6 pi electron. Will you get 6? 4n plus 2 apply? Yes. If n is equal to 1, you will get 6. So it is satisfying Huckel's rules also. All 4 conditions are satisfied. Therefore, these compounds are also aromatic. Now, let us go to the third class. Cyclic structures. Cyclic, heterocyclic, non-benzenoid, cyclic, heterocyclic compounds. Non-benzenoid, heterocyclic compounds. Let us see the examples. This is furan, thiophene, pyrrole. Furan, thiophene, pyrrole. How many electrons here? 6. 6 pi electrons are there. 2 here, 2 here, and 2 pair of electrons. This is actually the lone pair, but this contributes to the resonance or to the delocalization. It is inside the ring. This won't contribute to resonance because it is outside the ring. So outside the ring, lone pair electron won't contribute to resonance, but those who are inside, those that are inside, they will contribute to resonance. So 1, 2, 3, 4, 5, 6 pi electron. Here also 1, 2, 3, 4, 5, 6 pi electrons. Here also 1, 2, 3, 4, 5, 6 pi electrons. Asking you condition number 1, is it cyclic? Yes. Are they planar? Yes, of course. Are they conjugated systems? Yes. Do they follow Huckel's rule? Yes. If you are putting N1, then you will get answer as 6. So they all satisfy Huckel's rule. So they are aromatic. They are aromatic. You can actually check the aromaticity here. You can actually check the aromaticity here. Let me show you. Otherwise, the aromaticity, okay. This electron would jump here. When this electron pair jumps here, this pair would go here. So now the electron has got delocalized here. Now this can come here. When this comes here, this can jump at this position. So now what would be the result? See, now this can jump here at this position, right? So when this jumps here, this pair it would go here, and this pair it would go here. Finally it can come here, and this oxygen can become again, the lone pair is restored. So the electron, as you see, is constantly it's delocalized. These 6 pi electrons are delocalized. Similarly is the case of thiophene, and similar is the case of pyrrole. So actually when you are seeing it otherwise, it is, you can see that how it is aromatic. Let us come to fourth category. Category 4, cyclic systems that are ionic in nature. Cyclic systems that are ionic in nature. Ionic in nature. Now let us see, look at this. Cyclopropenyl cation, cyclopropenyl cation. What is this? 1,3-cyclobutadienyl anion. Cyclopropenyl cation, 1,3-cyclobutadienyl anion. Okay. So look at them. How many? Is it cyclic? Yes. Is it planar? Yes. Is it conjugated? Yes. How many electrons are there? 2. 2 pi electrons are there. Is it possible to get 2? 4n plus 2 applying Huckel's rule? Yes. If you are putting 0, n is equal to 0, the answer will be 2. So this is actually aromatic. You can check the aromaticity here. Otherwise also, okay, this is positive. So this carbon will attract this bond here. So it would come here. This positive sign, it would go here, right? In the same way, this can attract here also. This double bond can be attracted here also. So when it is attracted here, the positive sign comes here, right? In the same way, this now will get attracted here. When this gets attracted here, this positive sign goes down. So you can actually see that with these 2 pi electrons are getting delocalized in this small ring. Okay, otherwise this is aromatic only. Here also, is it satisfying the 4 conditions? Is it cyclic, planar, conjugated? Yes. How many electrons are there? 1, 2, 3, 4 and 5, 6. This is inside the ring. 5, 6. So 6. Is it possible to get 6? Yes. If you are putting n is equal to 1, you get 6. So it also satisfies Huckel's rule. You can otherwise also see the aromaticity. It will come here. This bond will go here. This can come here. When this comes here, this electron comes here. This electron can go here. When this electron goes here, this bond can come here. So, right? So otherwise also it is aromatic. So we have seen aromatic compounds. Let us see non-aromatic compounds. Examples of non-aromatic compounds. Cyclic systems that are non-aromatic. non-aromatic. So let me show you this example first. What is this? 1,3-cyclobutadiene. 1,3-cyclobutadiene. And look at this. This is 1,3,5,7-cyclooctatetraene. It satisfies the first three conditions: cyclic, planar and conjugated. It is cyclic, planar, conjugated. But how many pi electrons are there? 4 pi electrons. Does it satisfy Huckel rule? Is it possible to get 4? It's not possible to get 4. So this does not satisfy Huckel's rule. Therefore, it is non-aromatic. This one, it is cyclic, right? But it is not planar, right? Because in the earlier example we saw that this actually exists like this. So it actually exists like this. So it is not at all planar. Right? It actually exists like this. Okay, so it is not at all planar. So otherwise also you can see how many electrons are there. 1, 2, 3, 4, 5, 6, 7, 8. 8. Can you get the number 8? No. You can get 2, 4, 10, 14, 18. But you cannot get 8 electrons. So because it does not satisfy Huckel rule and because it is not planar, this compound is non-aromatic or anti-aromatic. Dear students, I hope you have understood Huckel's rule. If you like the class and if you have understood it, please do not forget to subscribe the channel. Thank you very much.